Hi, and welcome to this talk on serializing data in Go. We'll look at how to evaluate, design, and implement your own serializers. So let's start by looking at why we are serializing data in the first place. So the most common scenario is to exchange data between applications. It can be RPC calls. It can be to persist in-memory data. It could be you are collecting data from multiple sources and you want to combine it into a single source of data. Or it can simply be that you have some existing data and you want to be able to access that even faster than you already are. So basically, what we're doing is we're persisting memory. So if we have a struct with some fields, we create an instance of this field that will be represented in memory by some bytes. So let's look at one way of persisting this. One of the methods that you probably already know is JSON. So in this case, we take the data here and we represent it as JSON, which we can store or we can transfer between applications. So let's look at a raw memory dump versus JSON. So first of all, the big problem is that the memory isn't platform independent. So you can have different struct alignment or you can have different engineness. Also, you still have to resolve pointers. So pointers to other pieces of memory needs to be included as well. Second of all, the memory doesn't really have any form of schema. You're simply getting the values as they are. You have no... The in-memory representation is quite hard to extend, so adding new fields will change the struct. Changing types is difficult. You don't have any integrity checks. In JSON, you have some validation, but only on a structural level. So if a character changes within a string, you have no way of knowing, for instance. The in-memory representation cannot really be said to be any kind of standard. The in-memory representation is fairly small. It can be shrunken down a bit since typically there's some padding added to make memory accesses faster. But in general, it's quite compact. Compare that to JSON, which is quite verbose in terms of the data it actually represents. When dealing with raw memory dumps, you have no huge tools. You're basically writing them yourself. Whereas with JSON, there's plenty of packages available that you can use. But finally, there's a win in terms of speed. Or a pure binary representation will almost always be faster than a parsed representation, while parsed formats can be quite fast. There's an inherent overhead by having to parse the structure of the document and converting stuff to different types in memory. There's something in between. That is where you define the schemas for your data. Then you compile it and you get a Go equivalent of the schema that you're defining, and it will have marshal and non-marshal function attached to it. Then you have code-defined schemas, where basically you can define it in as Go, and JSON is a perfect example of that. JSON typically uses reflection to get from the Go code to the schema, but you can also have code generators that take the input and generate the similar marshal and non-marshal functions for your data. So if we take these serializers, we can put them on a gradient. So here's some examples. We have the schema-based generators that on the left. We have some in-between formats that are still binary but offer more features, but also typically adds a bit more size to your data. And you have the pure text-based, just as examples. This is not exhaustive, so there's a lot of others you can add to this, but this should give you like an idea of pure binary to pure text. So which one is better? That is a very common question, and I think it's also a wrong question to ask, because You can't simply rate them from bad to worse. It depends on a lot of factors that you should take into consideration when you choose a way to serialize your data. So let's go through them. So first of all, is the serializer standardized? Is it a standard that you can pick up? While I wouldn't say you should always pick a standardized one, it should be part of your consideration, because you might be using Go and a specific set of tools right now, but the more of a standard you use, the more likely it is that it will be readable in the future. Is it cross-platform? Same consideration. Is it something you can move from one language to another? How are the tools? How much effort should you be putting into updating and changing the structure? Can you extend the data that you're storing? So can you add more fields, add more values, add more block types, things like that? Does it stream? In many cases, you need to represent your data as an endless stream. So how well does the serializer fit into that schema? Of course, how is the speed? There's a base speed that you might need to achieve, especially when deserializing data. The speed can be important. Typically, it's not so important when you serialize the data, but of course, you don't want to spend extra CPU cycles to store something without getting any benefit. Similar, how is the size? And you may have special needs for your specific use case, so you need to investigate those. Let's take a look at a concrete example. So these are the things that we want to store. So we have a file with a name, a version, similar metadata that we want to store. We want to store a lot of these as a stream. They are pre-sorted by name, and there's a bunch of custom fields that may or may not be interesting. The primary use is that we want to be able to filter by name, and we want to forward to a specific entry. And since the stream is pre-sorted, that will allow us to forward to a specific point and list the entries from there. We want to be able to tell when we reach the end of the stream, so we must know that there's no further entries coming. So these are the requirements. So one of the things that came up pretty early is that we want to be able to skip these metadata blocks. So what we came up with is a very simple structure. So we have a name and we have the rest of the metadata as a serialized blob of bytes. So to serialize it very simply, you could simply write a string, you could write the bytes of the metadata. And as a simple example of reading it back, you simply check if there's more on the stream. You read the name and you read the bytes of the metadata. So we sit down to define a simple format for this. We add a version as the very first byte that you encounter. We then go through the incoming files. We write a Boolean true if there's more entries. When we're done, we write a false that indicates the end of stream, and then we simply add the two values to the stream. So as an example of how you could write a string, this is an example. So you write the length of the string and you simply append the value of the string to your output. So this is only an example. You can find a lot of packages that actually have these built in and can help you to write these types without you having to write your own primitive serializer. Let's look at some tips and tricks. Sometimes you want to add a header or identifier to know that this is the type you expect. That is only really needed if you are dealing with external data, I find. The thing you always want is to add a version, though. That allows you to upgrade the format in a predictable way and allows previous versions to be rejected by older deserializers. Sometimes a checksum can be helpful, maybe on parts of the data, not the entire stream. If you're making a stream, try to make individual parts skippable. So it's pretty quick to skip over things that aren't interesting. Try always to have an explicit end of stream. That way you know your input hasn't been cut off and you're simply landing at the end of an object or whatever. So don't rely on end of file being the end of the stream. Otherwise, you might get into situations where you think you have the entire stream, but you don't. Allow concatenating different streams. So even if you have a full stream, allow a new stream to be appended to it and the parser being able to continue from there. Also, no input should be able to crash your deserializer. Keep track of huge allocations, especially if you're receiving data from the outside. So with serializers, where the size of arrays, for instance, are defined up front, also keep track of huge allocations. This is if you are receiving data from the outside. If arrays are defined up front in terms of size, maybe have some way of controlling the size of those. That way, people can't send data to your server that will cause it to allocate huge amounts of data and thereby crash the server. Finally, make it concurrency friendly. In the example before, you can simply cut out the metadata and you can decode the metadata in separate Go routines. That will allow you to deserialize much more quickly, since the deserializer can chop up pieces and send it to other parts of the system to be decoded. So you might need to make an API for decoding objects. The standard library has an interface. Marshall binary, which returns the data of the object. Unmarshall binary that takes the data and puts it back into the object. I tend to modify that a little. So for marshalling, I tend to make it append to an already existing input. So when you marshal, you append to the slice you are getting and you return the combined slice. Similar, I prefer a small change to unmarshal, where it returns the remaining data that it might have gotten. So if it got extra data, then it will return the extra data. So for streams, I'm a bit more flexible. So what makes sense in your scenario is generally what I would recommend. Something that could work is that you have a writer where you write the serialized output to, and you simply have a channel of objects where you send objects to be serialized. For deserializing, you could have a function that receives the input, and you have a callback for every object that you get. You can do this whichever way makes sense for you. In other cases, you might want to have a reader or writer that holds the position on the screen and can be passed around. So you simply create a writer that writes all your serialized data to the output. The reverse, you give it an input and it provides functions to read back from the stream. Compression is something that often comes up. There's many different ways. A lot of people likes to compress individual elements. In the previous example, we could compress the metadata, for instance. I tend to prefer full stream compression, simply because it's simpler and also because decompression is usually quite fast. But when you do so, maybe consider adding the type of compression you use so you can switch that out on the fly. In general, though, the most important part is not to do it too early, because compressors are quite good at compressing even quite bloated output. So don't be afraid to write a little extra and have it picked up by the compression algorithm. That leads me to tests and benchmarks. So tests, first of all, always have regression tests, have a sample set that you know produces this output. Keep a collection of previous crashes, maybe have a zip file so you can make it easy to add more test cases as you encounter them. So if you have something that crashes, you can simply add it to a zip file and it will automatically be tested. Fuzz test is very obvious to use. It's amazing at finding subtle bugs, but it does take some getting used to setting it up. Of course, it can detect hard crashing inputs. Testing the encoding stage can be quite hard. So sometimes I set up a decode to encode to decode, where you then compare the decoded outputs. That is a way of getting your byte data into the encoder as well. But there may be other ways you can create good samples for your encoder to test. So now it gets tough. Benchmarks. And I'm sorry, your benchmark sucks. So I've seen a lot of benchmarks and there are a lot of similar mistakes in there. So a lot of them set out to determine the best serializer and deserializer. Thing is, it depends on your data. It depends on your data structure. So there's no one that is way better than everything else. So a lot of them test on one generic struct that they then throw at 20 different serializers to determine a winner. But it depends on your actual data and it depends on your actual structure of your data. So similar, they use this one struct with one set of values. So what you end up with is the CPU being able to basically predict everything going on. And you don't get a real world picture of how your serializer and deserializer is performing. A lot of them write to a fresh output, meaning that for every iteration of the serializer, you're basically reallocating the entire output. Don't include those, but also you should still be sure that it includes the allocations that are actually required by the serializer and deserializer. So which allocations should it include? In my opinion, it should include the allocations that cannot be avoided. So it should match your real code and not a rosy or a way worse than can be expected in real life scenario. Finally, a very common mistake is that it measures megabytes per second. So if the benchmark measures megabytes per second, you are making the speed dependent on the output size. So that means that bigger output size means better performance. But that's not really how it works because we don't want big output size. We want high throughput. So we measure objects per second or whatever metric makes sense. So I collected a small checklist. Make your benchmark clear, make it realistic to your goals, use real data, reduce avoidable allocations, but also include strictly needed allocations. Evaluate data size outside your benchmark. It's a second parameter alongside the speed. Don't evaluate both at once. So finally, some recommendations. This is very superficial and just to give you an idea and get started to some extent. So JSON, well, we know it. It's easy to read. It has a schema inside the format. It's well established. It allows you to extend objects and add more fields. It's good for casual sharing. What are the cons? So it can be quite verbose. It will always require parsing. So to know the length of a string, you need to parse the entire string to get the size of it, similar with arrays and other types of data. There's no native streaming, though there are some extensions that allow it, like new line delimited JSON. There's escaped characters in strings that needs to be de-escaped, so to speak. Similar, you can't have raw binary data. It needs to be escaped or encoded in some way. Typically, the tools involve reflection overhead. It's not big, but for instance, since you don't know the sizes of slices and things like that, you can't allocate everything up front. So you will also have some extra allocations coming from that. GOB is an internal format for in Go. It includes schemas with serialized data. It is a binary format, so it's rather compact. It is convenient and easy to use in Go, and it does allow you to extend the types, add new fields, and it will work as you expect. So the main con of this is that it's Go only. That pretty much disqualifies it for my personal use, but for your use, it may be more acceptable to do that. It has medium speed. It's not super fast, but it's also not crazy slow or anything like that. It can allocate a lot. Some of the tests I run has a lot of allocations, which seems a bit odd, but definitely test it yourself. It does have a bit of reflection overhead. Again, it's nothing major, but the convenience comes at a small cost. Then you have serializers like protobuf, flat buffers, Captain Proto. They have explicit schemas. They're binary. They have static code gen, so you can generate code. All of them have very large language support, quite compact in size. Typically, they are fast. It can depend a bit, though. So let's look at some of the cons. I don't personally prefer to have explicit schemas. I like to define my data structures in Go, but that is sort of the trade-off you need to make it easily available to other languages. In most of them, you must manage compatibility between versions, though most of them have tools to help you with that. That said, the tooling can be tricky. At least I find some of them very tricky to set up and get working correctly. And the output doesn't always match good Go code, since it's generated and it's not made specifically for Go. So we have something in between called message pack. It is similar to a binary version of JSON, so transitioning from JSON to message pack is not that big of a deal. It has implicit schema, just like JSON, it's just in a binary format. You can convert any message pack to JSON, which makes it quite easy to print out debug information, things like that. There's a bunch of very good Go packages that can help you a lot with it. Some of them have static code gen that allows you to generate marshal and unmarshal functions from existing code. There are also reflection-based implementations, so you can choose what makes sense for you. An important thing compared to JSON is that it has binary embedding. So binary is just a memory copy to insert binary data. If we look at the con, it can be rather verbose because it includes field names for objects. It can be slow to skip forward, similar to if you want to skip an object inside JSON, you have to pass everything in between. Message pack sort of has the same issue. So if you want to skip an entire object, you need to pass in between. So then you have the fully custom option. Basically, you write everything yourself. You have full control. It's fast if you benchmark it and write it correctly. But it does require careful design, detailed documentation, extensive tests. There's no cross-language support. So it's a lot of work. If I need to write some stuff myself, I tend to prefer a hybrid do-it-yourself. So you utilize tools for complex structures, prefer type safety over just adding raw values. So when you add a string, you add this is a string of length this. Know the serializers that you're using. So the serializers you use, know what is its strength and weaknesses. Start by writing the deserializer. That will often give you an idea of how you should structure your data and what makes sense in your setup. Define clear limits, so sizes, things like that, maximum sizes, so you know what to expect in the future. Define that up front. You can always relax them later, but add some limits to your various fields and values. Keep your options open for your future. Maybe add types that can be skipped, but you can define the types later. If you're adding blocks and you add a block type, have some of the types be skippable so it can be passed by previous versions without being unusable. Document well. Also, a shout out to TinyLib message P. I've used that for a lot of my hybrids since it has tools for serializing basic types like strings, values, arrays, and makes it very easy and very performant to do so. Also remember that sometimes JSON and CSV is actually fine and the readability will actually help you in the future. So unless you need the performance and size of the other types, then they can actually work out quite well. There's a lot of good tools for these, so don't be afraid to use them. And with that, good luck, have fun, and thank you for listening. I hope it was useful. Feel free to reach out if you have questions. Also, shout out to #performance on Gopher Slack. Feel free to join. Also, there's a lot of great people that can help with a lot of performance related questions, including serializing data. So hope to see you there. Have a nice day.